3.3, completing the square. When an equation has the form y equals ax squared plus bx plus c, meaning it's in standard form, the constants used to sketch the graph are not obvious. To obtain these constants, we use the method of completing the square. We use this method when we cannot factor y equals ax squared plus bx plus c to find its roots. The method of factoring we're going to take a look at in the next unit, and so we will come back to that. But for now, I just want you to compare your standard form with a vertex form. So if I give you an example, y equals negative 2 times x minus 3 squared plus 4, we get lots of information from this. We know that a is equal to negative 2, so we have a vertical expansion of 2, and we have a parabola that opens down. We also know that p is equal to 3, remember opposite sign, and we know that q is equal to 4, keep the sign. That gives us a vertex which is at 3 and 4. We have enough information here to graph. Okay, so we'll start by plotting our vertex. Which is right here. We know our parabola is going to open down, so it's going to go in this direction. And we know that our expansion is by a factor of 2, so we're going to go over 1 and down 2, over 1 and down 2, and then over 2 and down 8, and over 2 and down 8, and here is our parabola. Okay, we don't need to know what our x-intercepts are, we don't need to know what our y-intercept is. Compare that to an equation in standard form. So let's say something like negative 2x squared plus 4x plus 5. We still know that a is negative 2, so we have a vertical expansion of 2 and it opens down. And we can also tell by looking at this, because y-intercepts happen when x is 0, that we have a y-intercept at 5. But not enough information to graph. We need to know what our vertex is. So what I'm going to show you next is how to complete the square, and using this method we can take an equation which is in standard form and we can write it so that it's in vertex form. Okay, so I'm going to do a little bit of an intro first, and then we'll take a look at our example. So just to show you what we mean by completing the square. So what I'd like you to consider is squaring a binomial, because that's our starting point. To square a binomial means we're going to take a binomial, so for example x plus 3, and we're going to square it. When we write that in expanded form, we have x plus 3 times x plus 3, and you know how to multiply that. You're going to use FOIL. Okay, so you're going to go x times x is x squared, x times 3 is 3x, 3 times x is 3x, and 3 times 3 is 9. And then when you combine your two middle terms, you will get x squared plus 6x plus 9. Now, last year you looked at a shortcut on how to do this, so we're going to review this. You're going to take the first term, and you are going to square it. So x to the second power is x squared. You keep the sign that's inside the bracket, okay, and it follows the x squared. Then you're going to double the product of 3 times x. So 3 times x is 3x, and you are going to double it to give you the 6x, which is your middle term right here. Why do we do that? We do that because if you take a look at our work for when we used FOIL to expand this, your two middle terms are identical, right? So 3x and 3x, you've got two of them. That's why you're going to double the 3x. Okay, this sign is always positive. And the reason for that is, regardless of whether this is a positive 3 or a negative 3, when you square that number, because that's your next step, it will always be positive. Squaring a positive number gives you a positive. Squaring your negative number gives you a positive. So positive 3 squared is 9, and you now have the product of x plus 3 squared. So let's practice that on another one. Let's say you've got x plus 7 squared. So square the first term, x squared. Keep the sign, plus. Take the product of 7 and x, 7x, double it, 14x. Next sign is always positive, and then take the 7 and square it, and you get 49. So when you square x plus 7, you get x squared plus 14x plus 49. Okay, so let's take a look at the process of completing the square. The idea behind completing the square is to take a binomial like this in the form of x squared plus a number times x, and finding out what the third term is so that you have a perfect square. Okay? So in other words, when I factor this, I'm going to get two equal factors. So what you do is you take the middle coefficient, which is 6, and you take half of it, which gives you 3. You square the 3, and you get 9. So notice it's the same as what we have up here, x squared plus 6x plus 9. When we factor it, we should get back to two equal factors. Okay, in this case, x plus 3 times x plus 3. All right, let's take a look at the next one. Even though your middle number is not evenly divided by 2, okay, it doesn't matter. Okay, we're going to take half of 5, and that gives us 5 over 2. We're going to square that. And that's going to give us 5 times 5 is 25 over 2 times 2, which is 4, and we have completed the square. Okay, we also need to know how to factor a complete square. The way to do that is you take your first term and you square root it. So we square root the x squared term. That gives us x. We keep this sign the same. And we take the last term, the third term, which is 4, and we square root the 4, and that gives us 2. Put it inside, put your x plus 2 inside a bracket and a square on the outside. Okay, so pause the video for a moment and try out these two questions. On the first one, complete the square. On the second one, factor, and then restart the video and see if you got that correct. Okay, so let's complete the square. We want to take half of 10, which is 5, and we want to square the 5, which will give us 25. So this is a perfect square now. To factor, set up your brackets and put a square on the outside. Take the square root of x squared, which is x. Keep this sign, which is minus, and take the square root of the third term, which is 5. So square root of 25 is 5. And you finished factoring. Okay? Let's compare that to the factored form of this. We'll do the same thing, okay? Square root the x squared, you get x. Keep this sign, it's plus. Square root the 25, and you get 5. Okay? So notice that when your second term is positive, you have a positive inside your bracket here. And when your second term is negative, you have a negative inside this bracket here. So this concludes our introduction. So let's try our first example where we take an equation which is in standard form, a quadratic which is in standard form, and convert that so that it is in vertex form. Okay, so we want to go from standard form to vertex form. Our first example, we're going to take a look at a quadratic where the value for a is 1. Okay, so we're going to complete the square when the leading coefficient a is 1. Our first step is to group our first two terms. Then inside the brackets we want to add and subtract the square of half the coefficient of the x term. group the perfect square trinomial, rewrite the perfect square trinomial as the square of a binomial, and then simplify. Okay, so let's write the equation to start with. So y equals x squared plus 16x plus 71. So the first thing we want to do is to group our first two terms. Okay, like that. Our second step is inside the brackets to add and subtract the square of half the coefficient of the x term. So we want to go y equals, inside the bracket, x squared plus 16x. We're going to add and subtract the same number and leave the 71 outside the bracket. Okay, so we're going to complete the square here. So half of 16 is 8, and 8 squared is 64. Okay, the reason why we add a 64 and minus a 64 is because plus 64 minus 64 is 0. It does not change the overall value of our quadratic. Okay, so second step is this. Next, what we want to do is group the perfect square trinomial. Okay, so we're going to go y equals, and we're going to rewrite this so that it reads x squared plus 16x plus 64. There is our trinomial grouped. There's no coefficient in front of this bracket, so the negative 64 can just be on the outside of the bracket. And so we have completed our third step. Okay, and then we want to rewrite the perfect square trinomial as a square of a binomial. In other words, we want to factor the perfect square trinomial. Okay, so set up your brackets with a square on the outside. Square root your first term. Square root of x squared is x. Keep the sign. It's positive. Take the square root of the third term, which is 8. So we have x plus 8 squared. And then while we're doing that, we can simplify negative 64 plus 71, and that would give us positive 7. Okay, so our next step is completed. Okay, so now you have the same quadratic but written in vertex form. And that completes this example. In example 2, we're going to do the same thing. We're going to convert a quadratic, which is in standard form, into vertex form. The only difference now is that our coefficient on A is not 1. Okay, so we're going to complete the square when the leading coefficient A is not 1. First step, group the first two terms and factor out the leading coefficient. Second step, inside the brackets, add and subtract the square of half of the coefficient of the x term. In other words, complete the square. Third step, group the perfect square trinomial. Next step, rewrite the perfect square trinomial as a square of a binomial. That means to factor. And then expand the square brackets and simplify. Okay, so the first thing that we want to do is we want to take our equation in standard form. We want to group the first two terms, and we want to remove the coefficient which is on the x squared term. Okay, so that means we want to factor it out. Okay, so we're going to factor out a 2. That leaves us with x squared minus 6x. Oh, this should be an 11, right? Okay, plus 11. Okay, so we've completed our first step. We've grouped our first two terms and we factored out a 2. Next, what we want to do is we want to add and subtract the square of half of negative 6 inside the brackets, called completing the square. So we're gonna start with this step here. We're going to go y equals 2 x squared minus 6x. We're going to complete the square, so we're going to go plus space minus space, leave the 11 on the outside. Okay, half of negative 6 is negative 3, and negative 3 squared is 9, so we're going to add 9 and minus 9. Okay, once again, the reason why we add and subtract the same number is because when we combine those two numbers, they give us 0, and we don't change the overall value of our original quadratic. Okay, so the next step is completed. In the next step, we're going to remove the last term from the brackets and combine it with the constant term. Okay, so at the same time, we're going to group our trinomial. Okay, so we're going to go y equals 2. I'm going to draw in a square bracket. I'm going to group my trinomial, which is here. Okay, so I'm going to group that. Okay, so what they mean by removing the last term from the brackets and combine with the constant, what they mean is we are going to multiply the 2 times the last term in the bracket, which is negative 9, and we're going to combine that with the constant, which is on the outside of the bracket. Okay, so what that does is it gives us this. We go 2, we can change our square bracket to a round bracket now. We're going to have x squared minus 6x plus 9. Okay, we still have plus 11. And we're going to go 2 times negative 9, which gives us negative 18, and we'll put it on the outside of the bracket. Okay, so we have multiplied this to get negative 18. All right, and now we're going to factor and simplify. Okay, so we're going to factor what's inside the brackets. So we write our bracket with a square on the outside. Square root the x squared, you get x. Keep the sign minus, square root the 9, you get 3. And then we're going to combine 11 minus 18, which is negative 7. And here you have your quadratic written in vertex form. Okay, that ends example number 2. In example 3, we're going to consider the function y equals negative 4x squared minus 24x minus 20. We're going to complete the square to determine the vertex, determine the maximum or minimum value of y and state which it is, then for what value of x do the maximum and minimum occur, and then verify that the two forms are equivalent. So we're first going to complete the square. Now this one's a little different because our a coefficient on the x squared is a negative number. So I'll just rewrite the quadratic. Okay, we're going to group the first two terms, and we are going to factor out the coefficient on the x squared term. So that means we're going to factor out the negative 4. Oops, that should be squared. Okay, and when I pull a negative out of this binomial, okay, the signs of both of my terms are going to become opposite. So what's negative becomes positive. So this will be plus. 4 goes into 24 6 times, so we get 6x. And I already know that I'm going to complete the square at this point, so I'm going to go plus space, minus space, close the bracket, and leave the negative 20 on the outside. Okay? Now, if you're not sure whether you have factored this correctly, then expand to see if you get back to negative 4x squared minus 24x. So you're going to go negative 4 times x squared, negative 4x squared, so you're right on that one. Negative 4 times positive 6x will give me negative 24x, so you're right on that. So the next thing we do is complete the square. We take half of 6, which is 3. 3 squared is 9, so we add 9 and minus 9. Okay, in the next step, we are going to group the trinomial. Okay, so I'm going to go -4 and then group my trinomial. And then I'm going to expand the -4 times the -9 and combine that with my -20. All right, so I'm going to go y equals -4 x squared plus 6x plus 9. And I have -20, and -4 times -9 is positive 36. Now I can factor my trinomial. So make my bracket with the square on the outside. X plus square root of 9 is 3, so x plus 3 squared. -20 plus 36 is positive 16, and here is my quadratic in vertex form. Okay, so A, complete the square to determine the vertex. So we've completed the square. The vertex is, your p-value is -3. Remember, opposite of the number inside the bracket, so -3. And keep Q the same, so positive 16. We know that because A is -4 and it's a negative number, that we have a parabola that opens down, and because it opens down we have a maximum, and the maximum value of y is our y coordinate on our vertex. Okay, so it's 16, so that's what we're going to put here. Okay, when does that maximum value of y occur? The maximum value of y occurs when x is -3. So that number should correspond to your x coordinate of your vertex. Okay, so we've answered B, determine the maximum or minimum value of y and state which it is, and we've also answered C, for what value of x do the maximum or minimum occur. The next thing we're asked to do is to verify, and we are going to do that using two methods. The first one is we're going to work backwards. So we take our parabola, or our quadratic, in vertex form, and we're going to expand and simplify to get back to our original standard form quadratic. So the first thing I want to do is square my binomial. I'm going to use my shortcut, so I'm going to square my first term, which is x squared, keep the positive sign, multiply the 3 times the x to get 3x and double that, so 6x. The second sign is always positive, square my last term, so the square of 3 is 9, and then plus 16. Then I'm going to expand -4 times x squared plus 6x plus 9. I'm going to distribute my -4. And that's going to give me -4x squared minus 24x minus 36 plus 16. And then combine my like terms, which are, this should be, at the end here, right? -36 plus 16. So what I get is -4x squared minus 24x, and -36 plus 16 is -20. The second way you can verify is by using your graphing calculator. Okay, what you want to do is graph both functions. You want to use identical window settings. And if you get the same graphs for the two forms, then they are equivalent. Okay, So I'm going to get my graphing calculator out. Okay, y equals, okay, I will first put into the calculator the standard form. So negative 4x squared minus 24x minus 20. And then I'm going to put in my quadratic in vertex form. So negative 4 bracket x squared plus 3, oops, not x squared, sorry, just x. There we go, x plus 3 squared plus 16. And what I'm going to do is I'm going to change the line that I'm going to use to graph with. So if you're using a TI calculator, you're just going to move the cursor to the far left of your screen, and you're going to put the cursor over the little dashes over on the side, or slashes, and you're going to go enter, and notice it's now thicker. And now we're going to graph. Oh, I need to set my window settings. Okay, so I've got a y-intercept at 16, so I'm going to go a little bit higher than that. Okay, I'll leave this the way it is. So I'm going to maybe put in 20 here and graph. And there we go. So I have two graphs that look exactly the same. Okay, so I verified using algebra, and I verified using my graphing calculator that these two equations are identical. In this next example, we're going to do an application problem. You are going to get a scenario where you will be expected to write a quadratic function to model a situation. The student council at a high school is planning a fundraising event with a professional photographer taking portraits of individuals or groups. The student council gets to charge and keep a session fee for each individual or group photo session. Last year they charged $10. Just going to highlight that because that information is important. They charged a $10 session fee and 400 sessions were booked. In considering what price they should charge this year, student council members estimate for every $1 increase in price, they expect to have 20 fewer sessions booked. You've been asked to write a function to model the situation. What is the maximum revenue they can expect based on these estimates? What session fee will give that maximum? How can you verify the solution? And what assumptions did you make in creating and using this model function? Okay, so let's start by coming up with a function to model this situation. If we want to determine how much money student council is going to make, then we need to know what the price of each session is going to be, and then times that by the number of sessions that they are going to expect. Okay? So in determining our let statements, I'm going to let R represent the expected revenue. In dollars, and I'm going to let N represent the number of $1 increases. So in order to put together a quadratic function, we need to come up with our new price. Okay, so the price for this. Now, last year the price was $10, and they want to increase it by $1 increments. Okay, and we're going to let n represent every single $1 increment. So that means we're going to go 10 plus $1 times the number of increments that they would expect. And of course, I don't need to write the 1 in front of the n, so my new price is going to be 10 plus n. We also need an expression for the number of sessions. Well, last year they had 400 sessions. They figured that for every $1 increase this year, they would expect to have 20 fewer sessions booked. Okay? So my number of $1 increases is n, so I'm going to have 20n less sessions booked in this year. Okay? So now we have our price. And now we have our number of sessions. So we can write our quadratic function now. So the revenue is equal to the new price, which is 10 plus n, times the number of sessions that they expect, which is 400 minus 20n. Okay, so this is the quadratic that models this situation. In B, you've been asked what is the maximum revenue that they can expect based on these estimates, and what session fee will give that maximum. Now, whenever we use words like maximum or minimum, it means we want the vertex, okay? And because we want the vertex and our equation is written as a product of two binomials, we will want to first write this out into standard form by expanding, foiling. And then we want to complete the square to put it into vertex form. Okay, so we will start by expanding this by using FOIL. Okay, so we're going to go this times this. Okay, 10 times 2n, n times 400, n times negative 2n squared. So when I expand, I get 10 times 400, which is 4,000, 10 times negative 2n, which is negative 20, oh sorry, this should be 20, sorry, so that'll be 200n. N times 400, and n times negative 20, n, which will give us negative 20n squared. Now we want to rearrange this so that it's in standard form, so we need our squared term to be first, so we're going to rewrite this as negative 20n squared. We are going to combine our two middle terms, so negative 200n plus 400n is 200n, and then our constant at the end. Okay, so from our first two terms, we are going to factor out the negative 20. That leaves us with n squared minus 10n. We're going to complete the square, so we're going to go plus space, minus space, close the bracket, and put the 4,000 on the outside. Completing the square, half of 10 is 5, and 5 squared is 25. We are going to group our trinomial. And at the same time, we are going to multiply the negative 20 times the negative 25. Okay, so that gives us negative 20 times n squared minus 10n plus 25. Negative 20 times negative 25 gives you 500. And we're going to add that to the 4,000. Okay? Alright, so now we will factor our trinomial. So square root of n squared is n, square root of 25 is 5, keep the sign minus, and we're going to combine the 500 plus the 4,000 to get 4,500. So our vertex then is at 5 and 4,500. Okay? Now, according to our problem and our function, the first coordinate of our vertex is going to represent our n, okay, so the number of $1 increases, and our second coordinate is going to represent our revenue in dollars, okay? So we can now answer the question, which is, what is the maximum revenue that they can expect? So the maximum revenue will be $4,500. Okay, and what session fee will give that amount? So the session fee is our price per session, which is 10 plus n, and n is equal to 5, so we will substitute that in for n, and so we find that the session fee is $15. Okay, so maximum revenue $4,500, session fee $15. All right, so how can we verify this? Well, one way is that we can plug our equation into our graphing calculator and determine the vertex. Okay, and if you take a look at this example, okay, I've used the TI for this. Our vertex is at 5 and 4,500. Okay, so the vertex is at 5 and 4,500. This verifies that the maximum revenue is $4,500, and the session fee is, in this case, 10 plus n, which is 10 plus 5, which is $15. So the last thing that you've been asked to do is to, we can also verify one other way. We can also verify by setting up a table of values in your calculator. Okay, and if you take a look at our x values, they're going up. We've got 3, 4, 5, 6, 7, 8, and 9. And if you take a look at your y values, they're rising. Okay, we've got 4420, 4480, 4500, but then notice they're going down, 4480, 4420. So what this table is showing is the symmetry of your parabola. Okay, and you can see from it that the maximum value for y is at 4,500. So the table shows that the maximum revenue is $4,500, and the session fee is 10 plus n, which is 10 plus 5, which is $15. Okay, so the last thing that you want to take a look at is what assumptions did you make in creating and using this model function. So the price the Student Council sets will affect their revenue from this fundraiser as they have predicted in using this model. This model assumes that the price affects the revenue. And that makes sense, right? Maybe if you're going to increase your price, you're going to have less session fees, right? The revenue function in this situation was based on information about the number of sessions booked last year and predictions on how price changes might affect revenue. However, other factors might affect revenue this year, such as how happy people were with their photos last year and whether they tell others or not, whether the student council advertises the event more this year, whether the photographer is the same or different from last year, the date, time, and duration chosen for the event. So all of these factors can affect how many people are going to show up also to have their portraits taken. Okay, so 3.3 is now concluded.